Okay, so students, good afternoon. Today's topic is reduction of carbonyl compounds using sodium borohydride. Reduction of carbonyl compounds using sodium borohydride. So yesterday we discussed why sodium borohydride is a weaker reducing agent compared to lithium aluminum hydride. Okay, I have written some examples here. Then we'll discuss the mechanism. This is cyclohexanon. It undergoes a reduction with sodium borohydride, in presence of sodium borohydride, and it gets converted to this alcohol. Okay. Similarly, this aldehyde, the aldehyde is also gets converted to alcohol. Aldehyde gets converted to alcohol. Similarly, this acid chloride gets converted to alcohol, and there is addition of 2 hydrogen, removal of this halogen chlorine atom, chloride ion gets removed, and there are addition of 2 hydrogens here on this carbon. Okay. Similarly, this we have aldehyde again. It gets converted to alcohol. Aldehyde gets converted to alcohol. If you want to write these reactions, you can write these reactions. Okay. Now, sodium borohydride is used for selective reduction. Selective reduction because it is a weaker reducing agent. It cannot reduce all the carbonyl compounds, all the functional groups. It cannot reduce all functional groups. Like we can see here, it cannot reduce carboxylic acids, and it cannot reduce esters. This. So suppose this this molecule we have, in which we have this this ketone group and this ester group. So this ketone group can be oxidized, reduced by sodium borohydride. Okay. Here, I think I forgot to write. This will remain untouched. This will be reduced. So I have forgotten to write. It will become OH. Okay. So it is a selective reducing agent. Selective reducing agent. Suppose in a molecule, this molecule is given to us, and we have to reduce this one. We have to reduce this one, and this one should remain untouched. So we should use sodium borohydride. If we use lithium aluminum hydride will reduce this one as well. This one, the both functional groups will be reduced. Okay. Now we'll discuss the mechanism of reduction using sodium borohydride. Reduction of carbonyl compounds using sodium borohydride. Okay. So we have taken this cyclohexanon example. The first one, cyclohexanon example we have taken. This is borohydride ion. Borohydride ion. I have not written sodium. Sodium, we know that sodium is a spectator ion, just used for balancing. Just a balancing ion. Okay. So borohydride ion. This borohydride ion. Okay. And we know this, the boron has a negative charge, but boron has a negative charge, but this, we can say electronegativity of boron is lesser than electronegativity of hydrogen. Electronegativity of boron is less than electronegativity of hydrogen. I have written it may approximately this 2 or 2.1. Okay. So what will happen? There will be a polar, it will be a polar. So with respect to hydrogen, the boron will have a partial positive charge. With respect to hydrogen, it has a negative charge, but with respect to hydrogen, it will have a partial positive charge, and the hydrogen has a partial negative charge. Okay. And we see here this carbonyl group. The carbon is partially positive and oxygen is partially negative. This bond can can shift to the oxygen, because oxygen is more electronegative. So this will become an electropositive center. So this electropositive center, this hydride ion, a strong base, this hydride ion, okay, it can attack this carbon for bonding. So we have, see, we can see here. So this hydride ion, the hydrogen gets added to this carbon, and the oxygen gets a negative charge. Okay. Now from the solution in acidic medium, from hydronium ion, this oxygen will abstract one hydrogen from the hydronium ion, and there the water will be released. Okay. So this hydrogen and this oxygen will abstract one hydrogen atom from hydronium ion. Okay. And it will form the final product, the alcohol. It will form the final product, the alcohol. Okay. So there is, we can see there is one hydrogen addition to the carbon, one hydrogen addition to the carbon, and one hydrogen addition to the oxygen. Okay. But this hydrogen has come from sodium borohydride or borohydride ion. This hydrogen which is added to this carbon comes from the borohydride ion, comes from the borohydride ion. Okay. Did you understand? Hello? Hello?
Yes, sir.
Okay. Did you understand this mechanism? Is similar to like yesterday we discussed. Now we'll take another example of an acid chloride molecule. This is an acid chloride molecule, and this is, we know, this a carboxylic group. Carbon will have a positive charge and oxygen will have a partial negative charge. So this, because oxygen is more electronegative, so this bond can shift to this oxygen. Okay. There's again, so borohydride, from borohydride, hydrogen will attack the carbon. Hydrogen will attack the carbon. This hydrogen gets added to this carbon. I have shown here this carbon. This hydrogen gets added to this carbon. Okay. Now what happens? We can see in this molecule. Okay. This molecule, this is not a better living group, this R or alkyl group. Even hydrogen is not better living group, because if it will form a hydride ion, and which is highly unstable. This will also be a highly unstable. Okay. So they are not they cannot leave this group. So this if this chloride ion, if this chlorine molecule leaves this substrate, it will form a chloride ion which will be stable. So this chlorine leaves the substrate. Okay. And this bond, this double, extra discharge present on oxygen collapses back to the oxygen and carbon, formation of carbon oxygen double bond. Okay. See, so we get an aldehyde. Okay. An aldehyde here. Again, the same procedure follows. So borohydride ion, one hydrogen will attack the carbon. This bond will go to the oxygen. Okay. You see here. And this now there are no better living groups. There are no better living groups, or there are no living groups. Okay. So what will happen? This oxygen will abstract one hydrogen from the hydronium ion. So this is second step. In first step, we have added sodium borohydride. Sodium borohydride, both water and sodium borohydride cannot be added together. So in first step, sodium borohydride is added, and in the second step, so this water is added. Okay. So hydronium ion, this oxygen will abstract one hydrogen from the hydronium ion. okay, and it will form the final product, the alcohol. We can see here two hydrogen, we can see here two hydrogens are added in case of in case of acid chloride ion. In case of acid chloride molecules, okay, there is removal of halide and addition of two hydrogen atoms, and the both hydrogen atoms, there this both hydrogen atoms are coming from the borohydride ion, okay, and this hydrogen comes from the acid hydronium ion. So this was the reduction of carbonyl compounds using sodium borohydride. This is over. If you have any doubt, you can ask. We'll start another topic. Hello? These are few reactions. If you have any doubt, you can ask. Robin, Niharika, Rose. Hello? Are you listening?
No doubt, sir. Yes, sir.
If you have any doubt, you can ask.
No doubt, sir.
Okay. So I think I'll finish this and then I'll move to the other new share. We'll go to 5th unit. Don't mind the date. Last year I had prepared these slides. Okay, the same I'm going to use after doing some slide modifications. So this is first topic of 5th unit. The 5th unit deals with spectroscopy. Okay, so in this spectroscopy 5th unit, the first topic we are going to study or we are going to discuss is ultraviolet UV, ultraviolet visible, UV visible spectroscopy. Okay, UV visible spectroscopy. So first we need to know what is spectroscopy. Okay. Okay. So what is spectroscopy? So spectroscopy, it is the branch of science that deals with the study of interaction of matter with light. Study of interaction of matter with light. Light means electromagnetic radiation. How this electromagnetic radiation, what happens when electromagnetic radiation interacts with matter? What happens when electromagnetic radiation interacts with a matter? Okay, or it is a branch of science that deals with the study of interaction of electromagnetic radiation with matter, the same thing. Okay, now before going to the principle and other aspects, we should know the electromagnetic radiation, the electromagnetic radiation. Okay, so what is electromagnetic radiation? What do we know? What do we understand by electromagnetic radiation? Electromagnetic radiation consists of discrete packages of energy which are called as photons. The energy which is coming directly from the sun, it comes in discrete packages. It comes in discrete packages, not continuous, discrete packages, which are known as photons, Photons are different than phonons. Okay, so this energy comes in the form of photons. The photons are discrete packages of energy. Okay, a photon consists of an oscillating electric field, E, and an oscillating magnetic field M, which are perpendicular to each other. The electric field and the magnetic field This electromagnetic radiation is consists of electric field and magnetic field, and the electric field and magnetic field both are perpendicular to each other. They are perpendicular to each other. Okay, you can see here the electric field, the magnetic field. This is source, and this is the direction of propagation. So all three are perpendicular to each other. All three are perpendicular to each other. The direction, the magnetic field, and the electric field perpendicular to each other. Okay. Electromagnetic radiation. What are there are uh, some aspects we should know about electromagnetic radiation. Okay. Frequency. Frequency. This is exactly nu. Okay. We call this nu. This one. Okay. Frequency. So it is defined as the number of times electrical field radiation oscillates in 1 second. So this is known as frequency. What is frequency? The number of times electric field radiation oscillates in 1 second. What is the unit? The unit for frequency is hertz. 1 hertz is 1 cycle per second. 1 cycle per second oscillation, 1 cycle per second is known as 1 hertz. Okay. Now wavelength lambda. Wavelength lambda. It is the distance between two nearest parts of the wave in the same phase. Means the distance between two troughs or two crests. The difference between, because this is our wave, oscillating wave. So this difference between two troughs, or the difference between these two crests, are known as wavelength. This one. Did you understand? This one. The distance between these two crests. Okay, the distance between two nearest crests or troughs. These two crests or these two troughs. The wavelength. Okay, so what is the wavelength? It is the distance between two nearest parts of the wave in the same phase, such as distance between two nearest crests or troughs. Understood? See here, the same. This is amplitude, the height. This is wavelength. The two crest, the distance between two crests. Okay. The relationship between wavelength and frequency can be written as C is equal to nu lambda. It is C is equal to nu lambda. C is equal to nu lambda. Okay. As photon is subjected to energy, so E is equal to h nu. We know that E is equal to h nu, and this nu is equal to C by lambda. What is nu? Nu is equal to C by lambda. This we know. Okay. C is the speed of light, and lambda is the wavelength. Nu is the frequency. E is the energy. Okay. So this is our electromagnetic radiation or electromagnetic spectrum. We are concerned mainly with these two things. We are concerned with these two things. this UV visible and IR region. UV visible and IR region. UV visible from 190 to 750. UV visible, both ultraviolet and visible spectrum. I'm talking about ultraviolet and visible spectrum, nanometer. Okay. And IR is equal to 750 or 700 or 750 to nanometer. This is nanometer to 1 millimeter wavelength. Okay. So this, we are concerned with these two spectrums, UV visible and IR spectrums, because we have to study about UV visible spectroscopy and IR spectroscopy. Okay. Again, the same UV visible spectroscopy and IR. IR is divided into three regions: far IR, mid IR, and near IR. When we will discuss the IR spectrum or IR spectroscopy, there we'll discuss about these three regions. Okay. Right now we are mainly concerned with ultraviolet and visible region. So we can see here ultraviolet 190 to 400 nanometer or 440 nanometers, and visible spectrum 442 or approximately from 400 to 700 nanometers. It can go up to 750 nanometers. Okay. So this invisible spectrum, in the visible spectrum, just wait. Just wait. Okay. So in this electromagnetic radiation, visible region, you know about this, the visible spectrum: red, orange, yellow, green, blue, indigo, violet, or what we call this as VIBGYOR, VIBGEYOR, VIBGYOR. Okay, VIBGYOR region. So this violet region 400 to 420 nanometers, indigo 420 to 440 nanometers, the wavelength of this. Okay. Blue 440 to 490 nanometers, green 490 to 570 nanometers, yellow 570 to 580 nanometers, orange 585 to 620 nanometers, and red 620 to 780 nanometers. Okay, this range will not be asked, but UV visible range, UV visible range of UV and range of visible spectrum, they may be asked. It may be they may ask. Okay. And the similarly in IR spectrum, the reason, the spectrum IR reason, they may ask. Okay. But we should know this. Now we'll discuss about the principles of spectroscopy. Absorption spectroscopy, an analytical technique, which is concerned with the measurement of absorption of electromagnetic radiation. So what is absorption spectroscopy? It is concerned with the measurement of absorption of electromagnetic radiation by a matter or by any matter. Okay. For example, UV 190 to 400 nanometers and visible 400 to 750 or 800 nanometers. So spectroscopy, UV visible spectroscopy. This is UV visible spectroscopy. So the absorption of electromagnetic radiation in this range, or okay. And then IR spectroscopy, as we had discussed, 700 here it is written 760 nanometer to 1 millimeter. Okay. Then we have emission spectroscopy, an analytical technique in which emission of a particle or radiation is dispersed according to some property of the emission, and the amount of dispersion is measured. This we are not going to discuss in our, this is not there in our syllabus. Okay, but we should know what is emission spectroscopy. Okay, for example, mass spectroscopy. Now we'll discuss interaction of electromagnetic radiation with matter. Interaction of electromagnetic radiation with matter. Interaction of electromagnetic radiation with matter. So interaction of electromagnetic radiation with matter. We have different electronic energy levels. At room temperature, the molecules are in the lowest energy levels, E0. At room temperature, all the molecules are in the lowest energy levels, E0. We can see here this one, E0. Okay, but when the molecules absorb UV visible light from electromagnetic radiation, not only UV visible light and other IR or microwave, anything they can absorb. So when the molecules absorb UV visible, we're talking about UV visible light from electromagnetic radiation, one of the outermost bond or lone pair electron bond or lone pair electron is promoted to higher energy levels or higher energy states such as E1, E2, and up to En. It can go up to En, etc. is called as electronic transition, and the difference is as, this is known as electronic transition. Already we know this electronic transition. Okay, when the electron absorbs light, it can go from lower energy level to higher energy level, which is known as electronic transition. Okay, and the energy difference, we know this energy difference, delta E is equal to H nu is equal to En minus E initial, E final minus E initial. We can say E final minus E initial. This E final minus E initial. Okay. Okay. So this we know already. Okay. Now we have vibrational energy levels also. Vibrational energy levels, when molecules absorb electromagnetic radiation in IR region, they start vibrating. Okay, and because of this vibration, they tend they have different vibrational energy levels. Okay, these are less energy level than electronic energy levels. These are less energy levels than electronic energy levels. Okay, the spacing between energy levels are relatively small. The energy difference is very small. For example, when IR radiation is absorbed, molecules are excited from one vibrational level to another, or it vibrates with higher amplitude. It starts vibrating with higher amplitude. It starts vibrating with higher amplitude. Okay. Then we have rotational energy levels also. These energy levels are quantized and discrete. These energy levels are quantized and discrete. The spacing between energy levels are even smaller than vibrational energy levels. They are too smaller than vibrational energy levels. Okay, so we can see here this rotational energy levels are lesser than vibrational energy levels, and vibrational energy levels are lesser than electronic energy levels or electronic transition levels. Okay, so these three we have. Okay, clear this. Now we'll discuss about Lambert's law and Beer's law and Beer-Lambert's law. This derivation is not there in our syllabus, but we should know, we should be able to understand what happens when an incident light passes through a solution. Okay, So this Beer-Lambert's law states the relationship between the concentration of the solution present in a sample cell and the length of the sample cell. Okay, we'll discuss about this. So Lambert's law. First, we have Lambert's law. Okay, this. So when a monochromatic radiation, remember this, monochromatic radiation. Okay, so when a monochromatic radiation is passed through a solution, when it passes through a solution, suppose this is a cuvette, okay, and this is our radiation, it passes through, this is our incident light, okay, and this is the intensity after